April 25th, 1986 began like countless other operational days at the Chernobyl nuclear power plant. Reactor No. 4 was scheduled for a routine shutdown. Maintenance periods were standard procedure in any nuclear facility. Equipment required inspection. Systems required calibration. Tests were often conducted during these intervals to improve safety protocols. On paper, what was about to happen was not extraordinary. The engineering team planned to conduct a turbine rundown test, an experiment intended to answer a simple but important question. If the plant lost external electrical power, could the residual rotational energy of the steam turbine generate enough electricity to keep coolant pumps running for the critical seconds before emergency diesel generators activated? It was a bridging measure, a gap between primary power loss and backup system startup. The test had been attempted before but had not delivered satisfactory data. This time, managers wanted conclusive results. Earlier that afternoon, operators began gradually reducing reactor power in preparation for shutdown. Reactor output decreased steadily, and conditions appeared normal. Then an external variable intervened. The regional power grid controller in Kiev requested that Chernobyl continue supplying electricity longer than planned. Demand across Ukraine remained high. The shutdown was postponed. For several additional hours, Reactor 4 operated at mid-level power instead of descending smoothly towards shutdown. This delay would prove critical, because nuclear reactors are not static machines. Their internal chemistry changes over time. Fission products accumulate. Neutron absorbers build up and decay. Stability depends on timing as much as on engineering. By the time operators were authorized to resume the shutdown sequence late that evening, the reactor's internal conditions were no longer ideal. At approximately 11 p.m., the power reduction continued. The intended target was around 700 megawatts thermal, a level considered low but manageable for the planned test. Instead, something unexpected occurred. Power dropped sharply, far below the intended level. Instead of stabilizing at 700 megawatts, output fell to nearly 30 megawatts. This was dangerously low. At low power, the RBMK reactor entered a condition known as xenon poisoning. Xenon-135, a powerful neutron absorber, is a byproduct of nuclear fission. When power decreases rapidly, xenon accumulates faster than it burns off, suppressing the nuclear reaction even further. The reactor became sluggish and unstable. Operators faced a decision. They could abort the test, shut down fully, and report the anomaly, or they could attempt to restore power and proceed. Under pressure to complete the experiment, and confident in their understanding of the system, they chose to continue. To increase reactivity, control rods were withdrawn. Control rods are composed of neutron-absorbing materials. Inserting them reduces the nuclear reaction. Removing them increases it. Safety protocols require that a minimum number of rods remain inserted at all times to preserve a margin of control. That night, the margin was eroded. More rods were withdrawn than regulations allowed. Gradually, the reactor's output rose to approximately 200 megawatts, still below the original target, but considered sufficient to conduct the test. The configuration was now unstable. Cooling water flow remained high. Reactivity reserves were low. The reactor was operating outside normal parameters. Several automatic safety systems were disabled to prevent an unwanted shutdown during the experiment. The plant had entered a precarious state. Inside the control room, operators monitored analog gauges and indicator lights. The atmosphere was tense but not panicked. There was no perception of imminent catastrophe. To the staff, this was a complex but manageable technical procedure. At 1:23 a.m. on April 26, 1986, the final phase of the turbine test began. Steam flow to the turbine was reduced. As the turbine slowed, electrical output declined. Water circulation through the reactor core decreased. Inside the core, physics took over. As cooling efficiency dropped, water began to boil more intensely. Steam bubbles, known as voids, form inside the reactor channels. In most reactor designs, steam formation reduces reactivity. Water acts as both coolant and moderator. When it turns to steam, the reaction slows. But the RBMK reactor was different. It used graphite as its moderator and water primarily as coolant. When water turned to steam, neutron absorption decreased. Reactivity increased. This characteristic, the positive void coefficient, meant that under certain conditions, steam formation accelerated the nuclear reaction instead of dampening it. Power levels began rising. Operators observed fluctuations on their instruments. Within seconds, the increase became dramatic. Control became difficult. At 1:23:40 a.m., the emergency shutdown system was activated. The AZ5 button was pressed. This command triggered full insertion of all control rods into the reactor core. Under normal circumstances, this action would immediately halt the chain reaction. But the RBMK design contained a fatal flaw. The control rods had graphite tips at their lower ends. When inserted, these graphite displacers first pushed out neutron-absorbing coolant from the bottom of the reactor channels before the boron absorber section followed. For a brief but critical moment, reactivity spiked. In a reactor already unstable, that spike was catastrophic. Power surged uncontrollably. Estimates later suggested that output may have reached more than 100 times a reactor's nominal operating capacity. Fuel channels ruptured under immense heat. Water flashed instantly into steam. Pressure inside the core escalated beyond structural limits. At 1:23:44 a.m., a massive steam explosion tore through reactor number 4. The 1,000-ton upper biological shield, a concrete and steel lid, was blown upward. Moments later, a second explosion followed, likely fueled by hydrogen accumulation and additional structural failure. The reactor building was ripped apart. Concrete walls fractured. Debris was hurled across the facility. Graphite blocks from the reactor core were ejected onto the roof and surrounding areas. The nuclear core was exposed directly to the atmosphere. Inside the control room, confusion dominated. Some operators believed a hydrogen tank had exploded. Others insisted the core could not possibly be destroyed. The idea that an RBMK reactor could explode contradicted long-standing assumptions. Yet outside, flames illuminated the night sky. Ioni's eyes shimmered with a strange blue glow. The graphite moderator ignited, producing a fire that would burn for days. Radiation levels skyrocketed to thousands of times normal background levels. Dosimeters available in the control room maxed out at relatively low readings, misleading staff into underestimating the scale of the disaster. Higher capacity radiation meters were either locked away or unavailable. Within minutes, local firefighters were dispatched. They were informed that a roof fire required extinguishing. They were not informed that the reactor core lay open. They were not equipped with radiation protective suits. They climbed ladders onto the damaged structure. They stepped across radioactive debris. Some handled fragments of graphite, unaware they were touching pieces of a nuclear reactor core. Within an hour, many began experiencing symptoms: nausea, dizziness, metallic taste, burning sensations on the skin. Acute radiation syndrome had begun, though few recognized it immediately. Their efforts, however, prevented additional fires from spreading to adjacent reactor units. Meanwhile, in the nearby city of Pripyat, life continued. Nearly 50,000 residents lived just 3 kilometers from the plant. Some heard the explosion. Others saw a glow rising above the reactor building. Curiosity drew people to balconies and rooftops. Children slept. No evacuation order was issued. No sirens sounded. Radioactive particles drifted invisibly through the night air, settling onto buildings, streets, and playgrounds. Inside the Soviet administrative structure, reports traveled upward. Initial communications described an accident, but not total core destruction. Political caution slowed decisive action. Admitting catastrophic failure at a flagship nuclear facility carried enormous implications. By morning, helicopter crews surveyed the damage from above. What they saw was undeniable. The reactor core was open, a blackened cavity where the center of Reactor 4 had once been. Smoke rose steadily into the sky. The fire burned with a radioactive intensity that would contaminate vast regions of Europe. But during those first hours, the focus remained local. Extinguish fires, assess damage, maintain order. The full scale of the catastrophe was not yet understood, even by those closest to it. As dawn broke over Chernobyl on April 26, 1986, the Soviet nuclear dream had already fractured. The explosion was not merely a mechanical failure. It was a convergence of design flaws, procedural violations, systemic pressure, and a culture that assumed control where uncertainty demanded caution. And the consequences were only beginning.